Very good. So the next speaker is then Chamkaur Ghag and he's going to be talking about dark matter. Okay, please.
Yeah, so I'm going to sort of set the scene. So I'm not sure how many of you here are experimentalists, or how many of you are sort of in that sort of area, but there'll be almost almost zero, maybe zero mass. I kind of just want to set out the scene for where we are in terms of the experimental search, what we think is going on, or at least where the momentum is taking us, and why it's so valuable to be in a room like this. And then towards the end of it, sort of show sort of where we are. Hopefully there'll be a bit of time for me to get into more. In a room outside of here, I would say more speculative, but here more fun, let's say, interesting. Okay, but first, I just wanted to thank and honour Basil. I think he's, Spirit Basil carries on. He's probably up on some computer somewhere out there and looking down, very much enjoying this meeting. But it was nice that, so many, this room has so many of his favourite people. He's spoken to me, had met many of you, but I'd heard of you so much. Just through Basil, which is really great. So I'm very grateful for him to, great teacher and bringing so many of us together. All right, enough about Basil. So dark matter. This is now a 100-year-old problem, if you like, starting with Fritz Zwicky. We've got standard stuff. We've got the laser one. This year. You got the usual stuff of galaxy rotation curves and the observed. Sure, you're familiar with this jazz, right? The measure that the observed indicates that there's something like an additional gravitational contributor that would be non-visible, non-baryonic, non-standard model. That's what we'll come to see. But then there's more fun stuff, right? These are sort of showing the same thing we were touching on in terms of the evolution of simulations and large-scale structuring in the universe. And this is one that people like Carlos Frank used to show us a lot with and put a bet on, right? Saying who could spot the difference. But of course he'd lose half the time. It didn't really work. But here we've got surveys, and here we've got the simulations, the evolution of it. And this, the point I'm trying to make here, not it is that without some kind of dark matter component in these simulations, it just doesn't work. These structures don't form; they spin out very quickly as you try to form galaxies. And then there's some more. Then there's it was interesting just where Tumo ended there in terms of that 2.9 Z supernovae in terms of what we think is going on with the lambda CDM, right, and the sort of cosmological constants and so forth. Right? So here we see the angular power spectrum of the cosmic microwave background. This is essentially a picture of our universe as a baby. And then we can correlate, these what's going on here with densities, see if that it seems to fit this bill of fluctuations in the early universe, frozen in, so forth, right? But then the point is that when you actually break this down, you can fit this. And of course, famously, the curve, the fit is produced almost before some of this data comes out, and it matches very nicely. And you can get a bit of breakdown of the different components of what we think the universe may be made of. And then comes this thing, right? Things like the bullet cluster, which was very interesting because this kind of stuff is going to come along. It's really going to have something to say about things like MOND and plasma gravitational waves later. As Mark was alluding to, the gravitational waves and that being close to the speed of light, to say something about MOND as well. But picking all that apart, quite generally what we're talking about here is, okay, this is very hard to explain without some kind of additional matter. Also, we think. And is everyone familiar with this kind of image? Should I talk through this for a second?
I would love to hear about it.
Yeah, sure. So this is essentially the bullet cluster, and you've got two clusters of galaxies that are coming together. The gas and all the media is going to interact, and that will heat up and emit in the X-ray. So if you view that in the X-ray, you'll see on this jazz. And then if you gravitationally lens the system, you'll see that the dark matter and all the matter components come out with the stars, sort of kind of collisionless. And maybe you can do some fun, right? You could start to play with, could this be self-interacting dark matter? Was there any drag and kind of collisional form? All that kind of stuff in there as well. So people are breaking that down. But generally, this is another kind of one of those big bits of evidence. And of course, when I say big bits of evidence, to me, they're all kind of like 60%ers, right? None of them is a smoking gun. But they all kind of, have when put together, it becomes quite compelling, at least, to go after, to put together a picture like this. Where you're in that last slide the Tumo was showing, you see the terms in the DU that doesn't have the lambda m, the lambda z, and the lambda omega m and a mega lambda terms in it. But if we go to the sort of standard picture at the moment, this is the sort of thing you end up with, where our universe is very heavily dominated by these dark components, right? Dark energy, and then this dark matter bit. So I want to focus on this bit, which is it's quite inappropriate breaking all this up, but right, this is one that we at least have some models for, or some motivation for. Motivation for sort of how we might go after it. So dark matter, what could it be? Where does it fit? And I can go and ask my favourite theorists, what do you reckon? And they say, whatever you like. However many orders of magnitude you like, whatever scale you like, go fish. And so for a long time, still actually we've been focusing on sort of this sort of region, and this is where weakly interacting massive particles will land. Right, this is sort of the standard line is
What's that scale? Sorry, like 10 to the 10
mass.
Oh, that's the mass.
Yeah. Oh, sorry. Mass in electron volts.
Oh yes, sorry, no, up there.
Yeah. And the point is, you can go from black holes down to 10 to the minus 21. Right?
It was there, but
yeah. No. Lots of this stuff, or much less heavy stuff. But the thing I want to sort of draw your eye to is this, right? That for a long time we're focusing here, and this is kind of, for now, I'm going to show you why we've been focusing here. But this really comes from a few. One of them will be called the cosmic coincidence, and this kind of jazz, right? This is in the early universe. If you posit that there was some kind of dark matter born as a particle, and it's annihilating away, eventually with an expanding universe, you'll have some relic abundance freezing out. And the cross section for that interaction and the sort of mass, or the amount that you might get, tends to fit, loosely what we're observing today. So maybe there's some and these models, one of them was supersymmetry, very famously. That would give you a lighter supersymmetric particle, but actually there's tons of them, right? There's asymmetric dark matter, there's lots and lots and lots, right? But essentially, lots of extensions of the standard model, right? That try and deal with non-dark matter problems will end up with something that will have mass, that will be stable, and often will have weak interaction, right? So that's the give. We can say, well, maybe it has a weak interaction. Let's go try and find it if it does, if it's something like that, a WIMP. But whatever it is, there's a few ways of that we can think about going about it. We have accelerators, where we have we'll collide particles. We'll try and recreate the early Big Bang. Magic happens here, and then you get some dark matter particles come out, which of course we wouldn't observe in the LHC, but you might see the missing transverse momentum, or you might be able to scan and find the mediator, right? Which is another very nice way of probing this. The other way is just the inverse, right? Come the other way. Look at regions where there's high mass. Presumably there's a lot of dark matter there. The theory kind of the story goes, first comes the dark matter. Well, first comes the quantum fluctuations in the space-time, then comes the dark matter, then comes the baryonic matter. Right? So where there is the stuff we can see, there should be a lot of dark matter. So maybe we can just point our telescopes and satellites at it and pick up, annihilation of our dark matter particles into standard body particles, and things that we can readily see, positrons, neutrinos, gamma rays, whatever. And then this is the bit I kind of want to focus on for now. This is a direct detection. This is where we want to see our dark matter, if you like. If we've got dark matter around our galaxy or going through us all the time, if it's something like a WIMP, let's say we've got a TeV WIMP, right? Then there are lots of folk in the LHC that are still going, still motivated theories around a 1.1 TeV, very Higgsino type neutrino, right? So these things are all very much still alive. Something like that would imply, 100,000 of them going through a centimeter squared every second or so, right? At the 500,000 miles an hour as we're going around a galaxy. So we can play snooker, right, or pool with this stuff. We can see if we can get a dark matter particle come in and hit the nucleus of an atom and sense that weak interaction, and then measure the recoiling stuff afterwards. So that's the gig in terms of where we're going, kind of pushing down into this stuff. So the technology that's kind of leading the way and has done for a good decade or more is this liquid time projection chamber. I won't get into all of this again. I just want to. The point of this is to motivate, or just sort of expand on the motivation for where the current momentum is, right, and the current thinking. I'm going to jump right to the end, and I'll come back to this because then it'll make a bit more sense. Like, why are you showing me all this crap, right? Why are we not talking quantum physics and gravity? It's really because this whole thing's resting on Occam's razor. Sure, we'll say it's probably a WIMP. right? Dark matter particle, go find it, be done, then move on to dark energy. Gödel would say something different. Here we've seen a gravitational issue, and we said, quantum field theory, let's find the particle. Right? And in the past, that's fine. Right? We can collide stuff and we'll go find stuff, and that's all been motivated by quantum field theory in the first place. Right? We look for this stuff, go find the Higgs boson, there it was. What's that about? Right, that jump. So that's why I'm here. That's why I was very interested in Basil and all the work that everybody here does. And then, because this stuff can tie into dark energy as well, right? If we just get a bit deeper into what we're really talking about. So okay, I'll come to that stuff at the end. But let me just run through this quickly. So here, if we did have a dark matter particle and it did hit the nucleus of a xenon atom here, then we'd have something like the nucleus of that atom moving 1,000th of a hair's width. That's what we're trying to detect. But you do get a few photons from that, and you do get a few electrons liberated in that interaction if you put an electric field across what is effectively a bucket of xenon with some light sensors top and bottom. What it allows us to do is this technology allows us to sort of separate. This is our sort of discrimination parameter space. WIMPs would land here, things like borate, coherently scattering neutrinos off the nucleus. They would look very WIMP-like. They would sort of land here. But most of our background, or our standard model crap, if you like, that's all up here. And then you can play these games of, the way you configure these detectors and construct them in sort of Russian doll type configurations, so that you can beat back the backgrounds more and more and more and more until you've got a very, very, very clean core in the center of the detector. The current leading experiment is this thing, Lux Zeppelin. It's a mile under the Black Hills of South Dakota, so you get a mile underground, and then eventually you'll come to not this. This is up on the surface, but once you come underground, you'll see. You won't see this. I'll say actually, what you see is something more like this. But this is the kind of scale of the thing we're talking about. Photo detectors, and this thing took like 10 years to build, 250 people, etc., etc. Integrated. If I unfurl this detector, it's kilometers squared of surface area. Integrated over the whole thing. If we have 1 gram of dust, we're good. If we have 1.5 grams of dust total, we're screwed. Right? And the DOE tells us off very bad. So all that kind of madness means that in the center of the detector, so the center of LZ right now, the central 5.5 tons is by far the most radio pure, radio clean, radio quiet place to search for rare event physics. And that's on Earth, in Earth, I think the whole solar system, but I haven't checked that. So especially if you're doing nuclear recall type stuff, right? So that's again, what we're really doing is saying, let's try and create a space that's incredibly quiet and then see what happens, try and observe what might come on. And so a lot of work has gone into these kind of technologies. We've been scaling them from a few kilograms up to many, many tons. LZ is 10 tons of xenon total, and we do target, in that active volume, it's about 7 tons. And our physics is done in the sort of central 5 tons. Every single component, like cryostat, pneumatic transistor, or whatever, every single component, some a few thousand materials were screened for uranium, thorium, potassium. 5 years just to select materials and go to big manufacturers that produce titanium and say, please, would you mind stopping your production? We'd like to have it slightly cleaner. They say no, we go to somewhere else. And so lots and lots of stuff like that going on. And then here, this is the data from the experiment itself, just to sort of show you that, all right, it does work. Our standard model stuff up here, our calibration data sort of lands down here. And we can map all of this, figure out exactly what's going on. So this is, in terms of energies, I'm only showing you at the sort of few hundred keV scale, but this goes all the way down to at keV in terms of our background modeling. This is to show some how well we can fit the peaks and understand sort of what's going on in there. As I say, it goes all the way down, all the way up, so we can search, wide range. Over here, for example, is neutrino stubble beta decay. We can probe that with the same detectors, and we will do in the next generation of them. Okay, maybe I'll skip over this in the interest of saving time, but this is again just to say that we really have to. The whole gig is not. We're not really looking for dark matter. What we're doing is just characterizing our backgrounds. So it's the precision with which we can characterize our backgrounds, and then say something about the statistical significance of anything on top of it. Because we're not looking for a WIMP there or an axion, axioelectric effect, for example. If that existed, we can do physics with the electronic recall channel, sort of in this region, which is also where neutrinos, which stubble beta decay, all that kind of stuff would lie. Now that will give you peaks, nice little peaks. So that, it's easier to find. okay, this is kind of the energies again, sort of how low down. If anybody puts up a theory and says, look, well, actually, we need to find a 0.1 keV nuclear recoil, I'd say good luck with that, but maybe we can find something else. That's also where, for example, more insight and more understanding of what's going on, more messengers in our universe. Or there's things like the cosmic neutrino background there as well, right? I showed the cosmic microwave background, and we get lots of information from that. Cosmic neutrino background is probably just like, it's probably just normal distribution. We won't be able to tell anything, but anyway. But the point is, if you were trying to pick off those neutrinos, right, they're down whatever 1.7 Kelvin. It'd be down here. In principle, it's exactly the same technology, right? But no way you're going to have that hit a xenon nucleus and actually give you enough signal. So maybe we need quantum sensors. Maybe we need some better understanding of what might be coherent effects. All that kind of jazz, right? And again, that kind of ties into what's going on here. So that's a slight tangent to say there are other cosmic handles out there. And maybe we're getting into technology areas where you could find stuff. So this is some of the data from LZ. So you run these detectors in, you run it for as long as you can. This was a run that was a few months or so. But you run these things for about a year or so, having spent many years building them. And then you open up the data set, you unblind, and then you see if you've got anything in here. And if you haven't, well, now you can set an exclusion limit, another exclusion limit, right? So, but now we're the best at not finding dark matter. That's something. So this is where we are, right? So this is, but if you go back to what I said earlier in terms of the naturalness of the WIMP miracle, in the sense that the weak scale interaction in the early universe and the masses we're talking about, it's getting a little bit too weak. We're getting down into very interesting. In principle, this goes on forever, as with supersymmetry actually. Right? There's this notion that it's ruled out. It is. So there's lots more here, but even outside of supersymmetry, we'll show some. Okay, here are some other models and things like that, right? That show that here's where LZ is at the moment. There's more models. There's more models. There's more models. And so you can keep going on, right? But at some point, at least for me, having worked in this for a few decades, the WIMP is coming to its end, right? Once we're down to sort of the neutrino floor, there's an interesting thing that will happen around about here-ish, where this sort of technology will run into a background from atmospheric neutrinos and diffuse supernova neutrinos that will be coherently scattering off the nucleus and looking like this. So now you can say, it's not really a problem, give me more money, and I'll turn that into a background with a giant detector and then carry on. It's almost like your sensitivity with exposure will plateau for a bit and then carry on. But then the question is, who's going to fund that? That's many tons of xenon. And why? What would actually take us down there? Maybe we're smarter doing things like directionality, right? Getting some quantum sensing directionality and things that can actually tell us where things are coming from, and then we don't have to, play such a strong statistics in. But point is, there's still very much, there's room. There's an order of magnitude here. And actually, I said I've been in this 20 years. I've been waiting to get to this region, right? For a long time. It's been down to, okay, could be here, sure. When we get down to here, now we're in trouble, right? And that's where I've been wanting to get to. So maybe we find it, but maybe we don't. So for the next collaboration, there is a collaboration that is forming to get down to that neutrino floor. Because at some level it would be absurd, right? Spend all this money and all this tech and everything to get down to this and then miss the juicy bit at the end. It would be kind of silly. So, but this is being portrayed somewhat as almost the definitive WIMP search experiment, right? Or that weak interaction style experiment. It's more of an observatory actually, and it'll be this huge thing that can do all kinds of stuff, right? Supernovae and PP neutrinos down to some really nice sort of some percent sort of accuracy, lots of dark matter stuff there. But then what's really nice about this is that with this kind of technology, as you get larger, the backgrounds that come that are interfering with our signal, they're coming from the materials, right? Ideally what you want is just a floating magic ball of xenon touched by nothing. But of course we've got cryostat, we've got PMT, photomultiply tubes, all that kind of stuff. And that's where our radiation comes from. Now, xenon is quite dense, such that as you make it larger, we're just shielding that more and more effectively. So we get larger and our backgrounds go down. This is why the xenon technique sort of overtook from crystals and all the previous technologies that were out there a few decades ago, 15 years ago or so. You get larger, the sensitivity just improves, and of course you're getting more mass as well. So the chance, the cross-section property is increasing as well. So What that really means, though, is that as you get larger, as we go from LZ to XLZD, as we did from Lux to LZ and everything, each time we get access to more physics, more, more interesting stuff, for example. Things that you couldn't possibly have gone after with previous experiments in terms of dark matter type stuff. And then you can get into lots of neutrino physics there, which is cool. Okay, so how am I doing for time? So about like 5, 10 minutes?
Yeah, a few minutes, and then
All right.
we want to have discussion.
Oh, I shouldn't have asked. Okay, so coming back to this then, what else are we doing? So that everything I've told you, and that's pretty much the bulk of experimental particle physics now, right? That's the accelerator world and direct detection world. But then we're sort of coming down here as well, and then we're trying to push it out. Oh, sorry. Also axioms. I completely missed axioms. Apologies for those.
Yeah.
For the axiom fans, so I just didn't have time. So I thought I'd pick on one. But there's the same kind of gig going on here, right? We're focusing on so this might be microwave sort of cavity searches or something like that. There's a lot of focus again because we can. We understand it. We understand how we would go about doing this as we did here. This we understand as well, but how do you go about doing it? Well, this is where quantum sensors comes in, which is quite nice. And there's some work here that many in the room are involved in, know of here at UCL. This is where we're sort of levitating. It comes from Peter Barker's group, where they're levitating a nanosphere, quartz bead, nanobead, optomechanically with lasers. And this has ridiculous sense. I mean, it's a false sensor, right? Look at this funny and this reacts. But it's direction. So now we can tell where things are coming from, and you can start to play with it. This is not going to compete with 10 tons of Xenon in LC, right? But at low masses, at very, very, very low masses, it can. In fact, it outdoes it. And then there are lots of models that will have sort of coherent type effects. There's loads of self-interacting dark matter where this actually is very sensitive. So, and this isn't the only one. There's many experiments like this coming along, which is fun, but again, it sort of speaks to this sort of current paradigm, I don't quite call it old paradigm, that it is a particle and it will hit, right? Rather than, wait, what's going on with space-time and dark matter? What's this assumption of particles in space-time? What about process universes generating them both? What would dark matter have to say about that? Or what would folk in this room have to say about that? Because that seems a lot more natural. Okay, so this is the experiment itself. Let's flash it up here and then skip on. And that's this part. So if I go back to WIMPs, that's where we are doing. We're kind of spending a lot of time here. We're getting into this. Things like XLVD will be able to do things like this. We see asymmetry in the baryon sector. Why not the dark matter sector? And in principle, we could go after things like models of dark matter that will produce particles again, but they end up landing at a sort of few GeV range, which is annoying because it ends up landing right where boron-8 neutrinos are coming from the sun. So now you'd have to sort of decouple another effect that is itself not very well constrained when we have the potential for dark matter there as well. Put another way, we can't do beam on, beam off, right? Like accelerators. So that complicates all this. All right, but this is a kind of jazz that we can start playing with, especially if you start to get models that are going to give us. So Sunata's question as to in the dynamic universe, you still get gravitational waves. That's exactly the kind of thing I'm here for, right? In these models or whatever, what can you see? Where do you get? How do I go about looking for them? And so this is this is again talk about directionality, but dark matter with LZ and these kind of detectors, they ping, right? If something hits, just ping, 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 and then we look at our backgrounds, we make sure they weren't neutrons, it could have been dark matter, and we say, okay, we're confident this is WIMPs. Directional detectors would say, well, look, as we're moving around the sun, we're getting as we sort of drive towards Sagittarius, we could feel it with wind, right? Because that relative motion. So the idea, stepping back a second, is that we're moving, but the dark matter, the reason we're moving, we're rotating, right, is angular momentum conservation. As we sort of collapse and fall in, the galaxy would spin up and flatten. Dark matter doesn't need to do that as much. Right? It's not interacting in that way, so it remains a sort of halo all around us. And so we can, you can think of it as us sort of moving through a wind or driving into the rain. So if you can pick off directionality, if you can say, look, this event came from there, now we're golden, right? Now I can say, well, this is consistent with extragalactic, and this has to be background. Whatever I'm picking up here is rotating with my lab, so I don't care about it. So this kind of tech again is really very, very fun. So okay, in the last maybe 30 seconds, 'cause I've kind of already said it. The axioms assumptions, right? This is, we do not have von Neumann axiom, right? There isn't. It's like we saw something funny. What should we do? Well, let's find the particle. Be it the axiom, be it the WIMP, be it whatever, right? And that's kind of, you know, it's there's an assumption there that, and it may still be, but where they come from and why they will emerge, right? It's a bit too easy. And again, I've been working this. My bread and butter is this stuff, and it could still be WIMPs, right? I don't want to do WIMPs totally and say Cham says dark matter isn't WIMP. I don't know. But what I do know is that there is a process, right? Somehow we are going to create the emergence of something that looks like space-time and stuff moving in space-time, right? And even that's happening in two independent processes completely seems kind of absurd. Or they couple. And if they couple, well, dark matter's a very nice spot where they couple. Right? Observation and, you know, whatever is happening there in linking them. And also gravitational waves as well. All right, so can you spin, you know, Basil, you know, lots of times, you know, with Peter and Basil, we could sit there and we could play with some of this maths and start looking at stuff and bringing Coriolis, and then boom, there's dark matter. And I'd have to step back and say, oh, crap. So yeah, and then again, dark energy correspondence, you know, here we've got scalar field. Is it? We know we've got the Higgs field back there in the early universe. What is the Higgs field do? How is that coupling with dark energy in the early universe? What is happening there, right? At that same time when we're saying, well, the quantum fields are giving us all evidence, you know, these fluctuations in dark matter is going to fall in, we're ignoring a hell of a lot. Okay, okay, and then, so, I'll stop. Thank you.
So we have time for a couple of questions, please.
So this question is not as unkind as it's meant to come across, or as it's going to sound. I'm reminded in a way of supersymmetry, and actually, if you remember when you were being interviewed for your lectureship, one of the other people who's being interviewed was looking for supersymmetry, and I said, "At what point do you stop looking? What's the point where?"
What did you say?
Sorry?
Do you remember what they said?
There was about 30 seconds of silence.
Who was that, Simon?
Can't remember his name. He didn't get a job.
Was he not? Well, mate, Chamkaur.
The reason why I don't want it to sound unkind is because there's an awful lot of emotional inertia that goes into looking for a thing, and that point at which you say this specific thing with this specific instrument, beating down the backgrounds, and saying, to get beyond this, an order of magnitude more effort is required to understand the theoretical possibilities and build the detector. And
Not effort. You get the order of magnitude for free with very little effort with the scaling that we're doing the experiment.
but it
More money.
Yes, yeah. I mean, that's kind of what I mean by effort. So what's the route out? Because the effects, the galactic effects that you see, there's something's telling us something, but then we latch on in particle physics to say that particle answer would be really nice. So I'm curious to know at what point you would drop it and then move, and what direction you would move in.
Me personally,
Yeah.
I'm doing it. I'm right here. This literally, like you go for XLZD, and you end this gig. Right, WIMPs. If you still want to be WIMPs, then okay, I want to see why they're so getting so big. So theorists come and help me, right? Because I'm not spending another 10 years going an order of magnitude further. Given that the likelihood when I do all the loop corrections buys me nothing. Right? It's like going for the 1.1 TeV, you know, the Leszek sort of solution to dark matter. You can't do that for zero because you're just not going to get. You can't push that high. So which you build around a giant enormous going. So for me, it's XLTD, because now you've got the observatory. Now you've got the best humans can do in terms of the lowest background. It isn't just for WIMPs, right? There's the axions, there's neutron beta K, there's all that jazz, right? And you could just, and it can still be. That's the point. It's still a very, very, it's still the most sensible in that you can make sense of it. But as that's happening, you push left. You go this way, right, to get up this way. So as you're going left and lighter and lighter, there's more of them. So now you're playing up here in terms of parameter space. So now you can do that stuff, aeon, interferometry, all that kind of stuff, right? You can play with this. And then if you're still not seeing anything there, then you come here. Right?
I wanted to ask you, what if it's not a particle but a modification of gravity? I mean, not necessarily mod, but just to give an example, would your experiment also have a sensitivity to such a thing?
It would depend on what the expressions of that would do. So if it's something like something like higher dimensions or something like that, right? If it's in the LHC, you'd still be able to catch them potentially. If it's purely gravitational, it's absolutely, we get nothing whatsoever, then no. If there's nothing that can actually give us any kind of signal. But there are very few. If that were the case, then to my mind, that would just be an untestable theory. So
Like, what would be a untestable, a modification? Let's say a modification of Newtonian gravity.
yeah.
But with your technology.
Oh, with that, no. If you can't do this technology, then fine. But I guess I'm saying with liquid ion time projection chambers, you can't test MOND or something like that.
That was my question. Yeah. Okay.
But you can test some of the other sort of models depending on how they actually express, right? If it is, like I say, physical particles, that kind of stuff, in principle you could. And certainly the LHC you can. And then you can test even things like the Lisa Pathfinder going for gravitational waves can test MOND, can test MOG, right? And when it kind of goes past the chronology. So as long as it's testable somehow, me personally, I'm not wedded to this technology, right? It's just a good way of going after this. But as long as it's testable, we're good. But it may be that maybe that the only thing we could do is build a galaxy with dark matter and one without. In which case I'm out.
So we have Peter.
Yeah, sorry. Dark matter, does it interact with gravitational waves? Does it kind of...
What is dark matter?
Exactly. So that's why I'm wondering,
Yeah.
because if you...
Couldn't you answer that question? Dark matter is the thing that you can't see with light, with it's not emitting electromagnetic radiation.
Oh, sorry. Did you mean WIMPs, like a particular, or do you mean like the?
But the overall concept of dark matter.
Yeah. So my answer was to the overall concept.
Okay.
Well, no.
With WIMPs, you would...
But with some, depending on the actual model, though, then yes, then you could. So, for example, if it's primordial black holes, then absolutely certainly. And depending on kind of the particle nature or how they interact, then yes, you could go after them. But in terms of but more generally, given that we don't know what dark matter is.
That's it.
Yeah.
Okay. Okay.
But it should. It should. If it's particulate and everything, then yes, absolutely.
Okay, maybe we'll move on. Thank you very much.
Thank you.